Welcome to our microlearning channel. In today's video, we will discuss material science. Material science and engineering is a diverse field that studies the properties of various materials, including metals, ceramics, polymers, and composites. These materials are critical for developing new technologies across many industries, from aerospace to electronics to construction. Understanding the fundamental characteristics of different materials and how to engineer them for specific applications is the core focus of this discipline. The lab you see in the image is a typical materials science research facility, with equipment like electron microscopes and 3D printers used to analyze and prototype new materials. This introductory presentation will provide an overview of the key concepts, applications, and career paths in this exciting and impactful field of study. Atoms are the fundamental building blocks that make up all materials. Understanding the structure of atoms is essential for comprehending the properties and behavior of different materials. The arrangement of electrons in an atom, known as the electron configuration, determines the atom's chemical properties and how it will bond with other atoms. There are different types of chemical bonds, such as ionic, covalent, and metallic, and each type of bond influences the physical and mechanical properties of the resulting material. The strength of the interatomic bonds significantly impacts the material's characteristics, including its melting point, hardness, and electrical conductivity. Crystals have a highly ordered, repeating 3D arrangement of atoms, molecules, or ions known as a lattice. This atomic-level structure is fundamental to understanding the properties of different materials. This 3D rendering helps us visualize and study the geometric arrangement of atoms within the crystal structure. Techniques like X-ray diffraction allow us to analyze the atomic arrangement in crystals. Understanding the crystal structure is crucial for materials science research and engineering new materials with desired properties. Solids can have different types of imperfections or defects in their crystal structure. Point defects are localized issues involving a few atoms, like vacancies, interstitials, and substitutional atoms. Line defects, or dislocations, are one-dimensional defects that allow for plastic deformation of materials. Common dislocation types are edge and screw dislocations. Surface defects occur at the surface, like grain boundaries, external surfaces, and twin boundaries. Volume defects are three-dimensional, caused by things like pores, cracks, and inclusions. Diffusion is the movement of atoms within a material driven by concentration gradients. Atoms move from areas of high concentration to areas of low concentration. Diffusion requires energy to overcome interatomic forces, which is provided by thermal vibrations in the material. The rate of diffusion is influenced by factors like temperature, concentration gradient, and the type of material. Higher temperatures accelerate diffusion, while larger concentration differences result in faster diffusion. Understanding the process of diffusion is important for many applications, like material science, biology, and engineering. Mechanical properties are key characteristics that describe how a material responds to applied forces. Tensile strength is the maximum stress a material can withstand before breaking. Yield strength is the stress at which permanent deformation begins to occur. Elastic modulus reflects the material's stiffness or resistance to deformation. Hardness measures the material's resistance to indentation or scratching. Ductility indicates the material's ability to deform without fracturing. Toughness describes the material's capacity to absorb energy before it breaks. Grain size reduction is an effective way to strengthen materials. Smaller grains mean more grain boundaries, which hinder the movement of dislocations and improve overall strength. Solid solution strengthening involves adding alloying elements to the material's lattice structure. This distorts the lattice, making it harder for dislocations to move and increasing the material's strength. Precipitation hardening creates small, dispersed second-phase particles within the material's matrix. These particles act as barriers to dislocation motion, strengthening the overall material. Work hardening or cold working increases the dislocation density within the material. This makes it more difficult for dislocations to move, resulting in a stronger material. Phase diagrams are visual representations of the different phases and phase changes in a material as a function of temperature, pressure, and composition. They allow us to understand and predict the physical state of a material under different conditions. Phase transformations are the changes in a material's physical state, such as from solid to liquid or from one solid phase to another. Understanding phase diagrams and transformations is crucial for controlling a material's microstructure and properties, which is essential for many engineering applications. The image on this slide shows a detailed phase diagram for a binary metal alloy system, illustrating the complex relationships between composition, temperature, and the various phases present. This type of phase diagram provides a wealth of information that can guide the selection and processing of materials to achieve the desired characteristics. Iron is the primary component in ferrous alloys, which are widely used in construction and manufacturing due to their strength and affordability. Carbon is the most common alloying element, and adding carbon changes the mechanical properties of the alloy. Common examples of ferrous alloys include steel, cast iron, and stainless steel. Ferrous alloys are known for their good strength and toughness, as well as their hardness and durability. Non-ferrous alloys are metals that do not contain iron as a primary component. These alloys are known for their unique properties that make them valuable in various industries. Let's take a closer look at 4 key non-ferrous alloy groups: copper, silver, aluminum, and titanium. Copper alloys have excellent electrical and thermal conductivity, making them crucial for electronics and heat transfer. These alloys are widely used in wiring, motors, transformers, and heat exchangers. Silver alloys are valued for their superior electrical conductivity and resistance to corrosion. They are commonly used in high-performance electrical contacts and jewelry. Aluminum alloys offer a balance of strength, lightweight, and corrosion resistance. These properties make them ideal for aerospace and automotive applications, where weight savings are crucial. Titanium alloys have an exceptional strength-to-weight ratio and are biocompatible. They find use in medical implants, aerospace components, and high-performance machinery, where strength and lightweight are paramount. Ceramics are inorganic, non-metallic materials often formed from oxides, nitrides, or carbides. They are known for their hardness, high melting points, and resistance to wear and corrosion. Glasses are amorphous, non-crystalline solids that exhibit a glass transition temperature. Glasses are typically transparent, brittle, and resistant to chemical attack. Ceramics and glasses have a wide range of applications in industries like construction, electronics, aerospace, and biomedical. The image shows a beautiful ceramic mug with a smooth white glaze and a brown clay body, illuminated by warm sunlight and sitting on a wooden table. Polymers are large molecules made up of many smaller repeating units called monomers. The type and arrangement of these monomers determine the properties of the resulting polymer. Polymer chains can have different structures: linear, branched, or cross-linked. These structural differences impact important properties like flexibility, strength, and melting point. Thermoplastics can be melted and reshaped, while thermosets solidify permanently after initial heating. This distinction affects applications and recycling. Key polymer properties include tensile strength, elongation, modulus, density, and resistance to heat, chemicals, and solvents. Composite materials are formed by combining 2 or more different materials, resulting in a new material with enhanced characteristics. One material acts as a reinforcement, providing strength and stiffness, while the other acts as a matrix, binding the reinforcement together and transferring loads. These materials are used in a wide range of applications, including aerospace, automotive, construction, and sporting goods, due to their high strength-to-weight ratio and customizable properties. Common examples of composite materials include fiberglass, carbon fiber, reinforced polymers, CFRP, and wood composites. Corrosion and degradation are critical issues that can impact the performance and lifespan of materials and structures. We'll explore the key processes that can lead to corrosion and degradation, including electrochemical corrosion, stress corrosion cracking, erosion corrosion, polymer degradation, and ceramic degradation. Understanding these mechanisms is crucial for designing effective prevention and mitigation strategies. Electrochemical corrosion involves an electrochemical reaction between a metal and its environment, leading to the formation of corrosion products. Stress corrosion cracking occurs when a metal is subjected to tensile stress in a corrosive environment, resulting in the propagation of cracks. Erosion corrosion is caused by the combined action of corrosion and mechanical wear due to the relative motion of a corrosive fluid and a solid surface. Polymers can degrade due to factors like oxidation, hydrolysis, and exposure to UV radiation, leading to changes in their properties. Ceramics can degrade due to chemical attack, thermal shock, and mechanical wear, affecting their structural integrity. Electrical conductivity is a crucial material property that determines how easily electrons can flow through a material. Materials can be classified as conductors, semiconductors, or insulators based on their level of electrical conductivity. Metals like silver, copper, gold, and aluminum generally have very high conductivity due to the presence of free electrons in their structure. Semiconductors like silicon have conductivity between that of conductors and insulators, making them useful in electronic devices. Insulators like glass have negligible conductivity, effectively preventing the flow of electricity. The table shows the conductivity values for various materials, highlighting the wide range from highly conductive metals to insulating materials like glass. Magnetic properties of materials are an important topic in materials science and engineering. There are three main types of magnetic behavior we'll cover today: diamagnetism, paramagnetism, and ferromagnetism. Diamagnetic materials are weakly repelled by magnetic fields. Their magnetic susceptibility is negative and small. Paramagnetic materials are weakly attracted by magnetic fields. Their magnetic susceptibility is positive and small. Ferromagnetic materials exhibit strong magnetic properties and can be permanently magnetized. They have a positive and large magnetic susceptibility. We'll dive into the details of each type of magnetism and discuss some real-world examples and applications. Optical properties of materials are crucial in many applications, from lasers and solar cells to optical fibers and aesthetics. Well, these properties include reflectivity, transmission, absorption, and refractive index, which depend on the material's electronic structure and energy band gap. Understanding these optical properties allows us to design materials for specific purposes, whether it's maximizing light absorption for solar cells or controlling color and transparency for aesthetic applications. The image on this slide shows how a prism can split white light into a spectrum of colors, demonstrating the refractive properties of the material. Discussing the key optical properties and their importance in various applications will help the audience understand the significance of this topic. Thermal properties are important characteristics of materials that impact their performance and applications. Thermal conductivity describes how easily heat flows through a material. Good conductors like metals transfer heat easily, while insulators resist heat flow. Thermal expansion measures how much a material expands or contracts as its temperature changes. Different materials have varying expansion rates, which is crucial in design. Specific heat capacity indicates how much energy is needed to raise a material's temperature by 1 degree. Materials with high specific heat, like water, require more energy to change temperature. Thermal shock resistance measures a material's ability to withstand sudden temperature changes without cracking or breaking, important for applications with rapid temperature fluctuations. Materials characterization techniques are essential for understanding and evaluating the properties of materials. We'll cover 4 key techniques today: microscopy, spectroscopy, diffraction, and mechanical testing. Microscopy reveals the microstructure and defects within a material. Spectroscopy identifies the chemical composition and bonding of a material. Diffraction determines the crystal structure and phases present in a material. Mechanical testing measures important properties like strength, stiffness, and toughness. These techniques provide valuable insights that guide the selection and optimization of materials for specific applications. The key considerations for material selection and design include performance requirements, environmental conditions, cost and availability, and sustainability. When selecting a material, we need to carefully evaluate its strength, stiffness, and durability to ensure it can meet the desired function and performance. It's also critical to understand the operating environment, including temperature, pressure, and potential exposure to chemicals or radiation, to ensure the material can withstand those conditions. Cost and accessibility are important factors. We need to evaluate the material cost, production cost, and availability to ensure the design is feasible and economically viable. Sustainability is a growing concern, so we should assess the material's impact on the environment, including its recyclability, biodegradability, and ethical sourcing. By carefully considering these key principles, we can select the optimal material to meet the design requirements while minimizing environmental impact and cost. Additive manufacturing, or 3D printing, is a revolutionary technology that builds objects layer by layer using digital designs. This process offers many advantages over traditional manufacturing methods, including rapid prototyping, customization, and the ability to work with a wide range of materials. 3D printing has applications across many different industries, from aerospace and automotive to healthcare and consumer goods. The 3D printed object shown on the slide is a detailed, intricate design that highlights the precision and complexity possible with additive manufacturing. This technology is transforming how we design and produce physical products, opening up new possibilities for innovation and personalization. Nanomaterials are materials with at least one dimension in the nanoscale, between 1 and 100 nanometers. These tiny materials exhibit unique properties due to their small size, such as increased surface area, quantum effects, and enhanced reactivity. Nanotechnology is the field that involves manipulating matter at the nanoscale to create new materials, devices, and systems with improved properties. Nanotechnology holds great potential to revolutionize various industries, including medicine, electronics, and energy. Biomaterials are a broad field covering materials designed to interact with biological systems. This includes medical devices, implants, tissue engineering, and drug delivery applications. Key properties include biocompatibility, bioactivity, biodegradability, mechanical strength, and processability. Biocompatibility is crucial. The material must not elicit adverse reactions from the body. Bioactivity is also important, promoting beneficial interactions with cells and tissues. Other key properties depend on the specific application, but generally include things like degradation rate, strength, and ease of manufacturing. Smart materials are engineered to respond to changes in their environment, like temperature, light, or stress. They can change their shape, color, or properties in response to these stimuli. Intelligent structures incorporate smart materials to create systems that adapt to their surroundings. These structures can self-heal, sense damage, and even change their shape or stiffness. Examples include shape memory alloys used in self-repairing bridges and piezoelectric materials in sensors for structural health monitoring. The image shows a futuristic building with a dynamic, color-changing facade that responds to the time of day, creating mesmerizing light patterns. Sustainable material choices are crucial for minimizing waste and maximizing resource efficiency in production. Transitioning to renewable energy sources for manufacturing can reduce reliance on fossil fuels and associated emissions. Implementing water conservation practices and minimizing water usage during production is an important aspect of sustainable material management. Conducting life cycle analysis to assess the environmental impact of materials from extraction to disposal is key for making informed decisions about sustainable materials. Materials processing is the transformation of raw materials into useful forms. This involves a sequence of steps, each affecting the final product's properties. Manufacturing involves the production of goods, often using various materials processing techniques. The manufacturing process is crucial, ensuring efficient production, quality control, and cost optimization. This slide provides an overview of the importance of materials processing and manufacturing. Aerospace applications require materials that can withstand extreme environments, high temperatures, pressures, and harsh atmospheric conditions. Key materials include high-strength alloys, composites, and ceramics that can handle these extreme conditions. Lightweight materials are crucial for aerospace to optimize weight and improve fuel efficiency. Titanium alloys, aluminum alloys, and carbon fiber composites are favored for their excellent strength-to-weight ratios. Safety and reliability are paramount. Aerospace materials must exhibit high levels of durability and integrity. Non-destructive testing methods are used to ensure structural integrity and mission success. Advanced manufacturing techniques like additive manufacturing allow for complex designs and lightweight aerospace components. Automotive manufacturers are using a variety of advanced materials to improve the performance, efficiency, and safety of vehicles. Lightweight materials like aluminum alloys, composites, and high-strength steels help reduce vehicle weight, which improves fuel economy and acceleration. Corrosion-resistant materials like stainless steel, galvanized steel, and aluminum alloys are used in body panels, exhaust systems, and other components to withstand harsh environmental conditions. High-temperature materials like cast iron, nickel alloys, and ceramics are used in engine components, exhaust manifolds, and turbochargers to handle extreme heat. Durable and safe materials like high-strength steels, advanced composites, and airbag materials enhance vehicle crashworthiness and passenger protection. Materials like lithium-ion batteries are crucial for storing energy from renewable sources, enabling grid-scale energy storage and powering electric vehicles. Silicon-based solar cells are widely used for converting sunlight into electricity, with ongoing research exploring more efficient and cost-effective materials. Materials like platinum and palladium are essential components of fuel cells, which generate electricity through a chemical reaction involving hydrogen and oxygen. Materials with high thermal conductivity, such as copper and aluminum, are crucial for efficient heat transfer in energy systems, reducing energy losses. Biocompatible materials are crucial for medical devices and implants, as they minimize rejection and ensure long-term performance. Examples of biocompatible materials include titanium alloys, polymers, and ceramics. These materials are used in a variety of biomedical applications, such as bone repair and replacement, ophthalmic devices, and dental work. Hydroxyapatite and biodegradable polymers are used in bone grafts and scaffolds to aid in bone regeneration and fracture healing. Materials are used in contact lenses, intraocular lenses, and artificial corneas to restore vision and improve quality of life. Dental materials like composites, ceramics, and metals are employed in fillings, crowns, and implants to restore and enhance oral health. The field of materials science and engineering is constantly evolving, driven by ongoing research and innovation. And new materials and technologies are continuously emerging, promising to revolutionize various industries and address global challenges. Advancements in materials science are enabling more sustainable, efficient, and advanced solutions in areas like energy, healthcare, transportation, and electronics. In conclusion, materials science is a fascinating field that plays a crucial role in the development of new technologies and innovations. By understanding the behavior and properties of materials, scientists and engineers are able to create materials that are stronger, lighter, and more efficient. From everyday objects to cutting-edge technologies, materials science is all around us, shaping the world we live in. The future of this field holds immense potential for breakthroughs that can profoundly shape our world.